Assalamualaikum and good day, student. I'm planning to do my lecture 6 today with a FOC style, so enjoy your study. New topic to discuss is about relative motions, which is more on the moving particles and constraint dependence particles. Moving particles is more focused on the vehicles, something like vehicles, or people are running, cars moving, aeroplanes which is not connected, or there is no connected each other. Another one is a constraint dependence particle. It's some sort like pulleys, multiple pulleys connected with a string or connected with a belting. So each of the movement is really dependent each other. For moving particles, taking an example, there is a two jet A and jet B. Hold on, I'm putting the laser pointer out. Assuming there is a jet A moving at a certain path, flying at a certain flying path, and then jet B is flying at certain paths. So we want to know the exact position of the flying position of plane A and flying position of plane B. So this is the flying path of jet A, and then this is the flying path of jet B. So the jet is flying until point A and point B. So there is a ground controller over here at the ground at position O, we name it as O, is measuring or monitoring the position of plane A and plane B in order to avoid the collision. So an arrow and red arrow directing to the A is the name as RA, is actually the position, the vector position of plane A reflected to O, reflected to ground controller, while the RB and a red arrow directing to plane B is actually the vector position of B reflected to 0, to O, to ground controller. If we join another arrow from A to B, it means that it is a vector position of B relative to A. This is the arrow. This is the arrow of position vector of plane B reflected to A. From the previous explanation, it is either the words RBA in the other way of explanation is vector B relative to A, or vector B with respect to A, or vector B observed from A. So RB is actually the vector absolute position of B. RB is actually a vector absolute position of B, referring to O. Same applied to RA. And then when we look into the graphical or on the polygon, you can see that RB is equal to RA plus RBA. When we do it for a velocity of the jet, it is also according to a position equation. Same applied to the acceleration. From the equation just now, RB equal to RA plus RBA, when you are looking at this arrow, the green arrow, which is nearly to the right hand side, so this is actually position vector of plane B reflected to plane A. But when I change it to the left hand side, see what happened. It's actually the negative position of B reflected to O. Or if you don't want to write like this, you can write position of RA, position of RAB, meaning that position of A reflected to B, positive RAB. So the conclusion is RBA is actually RAB, meaning that B observed from A equal to A observed from B. The only difference is either the direction or negative. This is another example of relative motion. There is a Ferris wheel. Let's say there is a Ferris wheel over here in the amusement park, and then there is a vehicle moving at the ground from this position, moving right hand side to the position A. There is somebody at point O is looking into both Ferris wheel and car motion. So Ferris wheel is moving, rotating, and then the car is moving from one position to another position. So at this instance, what is the velocity of B relative to A? What is the velocity of B relative to A? You know that when there is a particle moving in a circular motion, at an instant point, there is a tangential velocity acting tangential at the point of B. So this is actually velocity of B. So since I want to compare it between velocity of A, so I put it at the zero position of X and Y axis, VBA. For me to ease calculation, to add with a VB and VA, so I break the main component of velocity VB into VBX and VBY. The car is only moving at the horizontal, which is only VAX. So to simplify, it's actually VAX plus VBY. But wait for a while, we see the equation first. So from the equation, VB is equal to VA plus VBA. This is the one that we are looking for. Velocity of B relative to A. So in matrix form, so we can start adding up the value of each of the velocity of VBX and VBY. We already break into the X and Y component. VAX and VAY, there is only X value, there is no Y value. Then you will get the velocity of B relative to A. In the matrix form. So what is the magnitude of VBA? The magnitude of VBA can be get from this equation. What about the direction? Direction, you can use your own imaginary tool from trigonometry to direct the positioning direction of the VBA. Just now there is a mathematical way. Now there is a graphically way on how to determine the velocity of B relative to A. Again, you know there is a velocity, tangential velocity at point B, and then there is a velocity horizontal velocity of VA. So when we put this VB and VA at the X and Y axis using a proper scale according to the magnitude of the VA and VB. So this is VB using scale, like say, and then VA according to scale, and then when I put another arrow towards B, which is velocity of V relative to A, by measuring the distance of this blue arrow according to the scale that I used previously when I want to construct this line, so I can get the value or magnitude of the VBA. So this is the direction actually. So VBA again is equal to VA plus VB. VB is equal to VA plus VBA. But how to find the acceleration of B relative to A? You know that at Ferris wheel, when it moves in circular motion, there is two kind of acceleration happen. One is tangential acceleration, another one is normal acceleration. For car, there is only one acceleration. So you need to add up all this value using matrix form. So this is the equation: AB equal to AA plus ABA. At AB itself, as I mentioned to you just now, there is a AB normal and AB tangent equal to AA and ABA. So you know that normal acceleration at this point acting to the center of circumference is accordance to this formula: V squared over R over rho. Rho is actually the radius of the Ferris wheel. V is the tangential velocity over here. So using the matrix form, you can get the overall or the acceleration of B relative to A. This is another example of a red car moving in a straight line, but meanwhile a blue car is moving in a curvature road with a radius of R. So what happened here is actually, there is acceleration of red car AB, and then there is a normal acceleration acting on blue car directly to the center of circumference, and then tangential acceleration. So same method as what you do on the Ferris wheel and a car. You need to do on the matrix form to calculate the relative motion of the subject. So constant dependent motion. In certain cases, the motion of a particle will depend on the corresponding motion of another particle. Okay, I think I will stop right now. This is actually I don't want to prolong the video, so I will stop this one. I continue for the constraint dependent motion at some other video. Thank you very much.